Good afternoon, everybody, and welcome to my talk about functions, compilers, and values. My name is Dawid Zalewski, and I'm very happy to see you all here at my talk. You most likely came here to hear something about what the title says, right? So I hope that you want to, or that your intention was to learn something about how compilers treat the objects that are passed or returned from functions, and how you as programmers can leverage those insights. And that's my intention, so hopefully it's also your intention. Now, why this talk? There are so many ways to pass and return objects. Those of you who came to the talk of Nico already have seen what universal references do and what this L-value references, R-value references, values do, and so on and so on. But this is not the end of the story. There is much more in C++ than just R-value references, R-value references, and pure values. And this talk actually was born on an idea that I got when I was preparing a workshop last year, which was about C programming language, also for the CppOnSea. And I observed something curious when I was passing objects to functions. That's how it came to being. Like in the very simple example that you just see on the screen, if you look at it, it seems obvious. Like if you just want to consume an object, like in this case, a string object, in a function, you pass it by const-reference, right? That's what we learned, that's what we are taught. There are more than possibilities than this. You can also pass by L-value, by R-value reference. Both of them can be constant. Some of them don't make much sense. You can pass by pointer. Many people still pass by pointer, a row non-owning pointer, which is something you shouldn't do, or simply by value. And the const at value doesn't make any sense, obviously. And now a question. And there are actually two questions. Do those functions look different when they are compiled? Is there any difference in the generated machine code? Who thinks it's different? Okay, who thinks it's the same? That's a trick question. That's why you raise the hand, I know. Which one is the fastest? Or which one is the slowest? Is any one of them like really slower? That's a very good answer. So one of them can be slower, but doesn't have to be. So it all depends. To answer your first question, the code gen will be the same. All of them will generate exactly the same assembly. From the point of view of the compiler, there is no difference. So I will give you a very short crash course in the assembly language very soon. For now, accept it at the face value. There is no difference in the generated assembly. We pass the pointer to the string character data. In the register, we pass the formatting string, and we call the function, and that's all. Now, there is a small difference, though. When you pass by value, the caller will create a copy first, before calling the function. But it's the caller job to create a copy of the argument you pass by value. It's not the callee. The code gen of the function itself, again, is the same. Now, what's even more surprising, as I said, it depends. So if you have a non-trivial type, which has your user-defined constructor or whatever that makes it non-trivial, definitely passing by value is slow, and you shouldn't do it because a copy will be created. But if you have a trivial object, like that one, it's the most trivial string I could come up with, that has value semantics, in that sense that when you pass it, a full copy of it is being made. It's not passed by a pointer, right? It's a struct. So when you have such a thing, most of the compilers will again generate the same code for the function itself. So by doesn't matter. We just accept some pointer on the stack. And it's the pointer to the character array. Sorry, it was too fast. Pass the formatting string, and so on. Your assembly may vary, but generally speaking, that's it. Now, most of the compilers will also optimize away the copy totally. There will be no copy being made. It will be one string created on the stack, and this string, or actually a pointer to it, will be passed to the function that you call. Most of the compilers, not all of them, and that's what this talk is about. How the compilers see the code and what are the differences between the compilers. A few takeaways. Trivial objects are a bit easier to optimize for the compilers, definitely easier. And compilers aggressively optimize way beyond what the standard dictates. So you will see things in the assembly that shouldn't sometimes, you might think, be there. Now the real start of the talk. It's a story about the compilers. So I use the two newest compilers, newest and the shiniest, the most popular open source compiler, GCC and Clang, in the newest version, both on the x64 platform, on the x86 platform, 64 bits, so compiling for Linux. By popular demand, let's say, I also use two other compilers. One, because it's targeted towards x86, that's the intercompiler. It does really heavy magic and heavy optimizations when it tries to come up with the best assembly, best machine code. And one, because that was a major complaint of me sometimes talking about compilers, MSVC, because this is a very popular compiler, right? Let's face the reality. So the MSVC in its newest version, all of them, thanks to Matt Godbold and his compiler explorer and his team. Flux, just for the completeness, all of them compiled under standard C++20 with all the warnings enabled, so code compiles with no warnings, and the maximum optimizations. So the compilers should do the work as good as they can. For those of you who are curious, I had to disable the stack canaries for the MSVC because it was really confusing me a lot. So one of these flags is disabling the stack canaries on MSVC. And here the talk really begins, to pass and return. There are so many options, like you can pass by value. We've already seen it. And we've already seen that some compilers heavily optimize it. Other pass by reference, by a pointer, by const-reference, r-value reference, whatever. In a way, everything is passed by a pointer. So you pass a pointer to a function, this pointer is accepted. Even if you think you pass by value, you don't really pass a value. You pass a pointer to a value. There are also many ways to return. Some of them maybe don't make much sense. Some of them might make a lot of sense. So you can return by reference, by pointer, or by value. To understand a bit how all of this works, because I'm going to show you some stack and heap pictures from time to time, you should first get some common understanding of what's going on when you really pass a value or return a value from a function, what the compiler does, what kind of code transformation it performs. The simplest function you can ever imagine, two long values that you declare, and they're passed to a function that adds them together and returns the value, the sum. Cannot be any easier, right? What really happens, of course, that's what we teach people who study computer science, is that those two values are going to be put on the stack in the computer, one after another. Then those two values will be, we don't really teach it, but that's how it works. They're put in the registers of the computer, in the RDI and RSI register. Important to know those two registers. They will come back a lot during the talk. So the caller copies the values into the registers and then calls the function. The function is a very short one, so it reads the values of those passed in these registers, in the RDI and RSI, adds them together and stores the result in the RAX register. That's the return value register on most of the ABIs. Finally, this 42 will be copied back by the caller on the stack. Now that's what we teach to students, that's what we teach in books, and that's not really true. Like any sane compiler with any optimizations enabled won't do anything with the stack. What will happen is very simply, everything will be just in the main function. Two values will appear in two registers, RDI, RSI. The main will do it. The function will be obviously inlined. There will be no function add anymore. And the main will call the add function and put the result in the array. So that's the basic optimization of what happens when you have such a simple scenario. Now for something more complex. That's the so-called oversized object. It's oversized because it doesn't fit in the computer registers. You only have a couple of registers that you can use for passing arguments. And if it's bigger, it doesn't fit anymore. A struct of 3 long numbers. And we repeat the same exercise. So pass it to a function that adds 2 vectors now together and tries to return the sum of them. Now, passing oversized objects works a bit different. Now the stack really begins to be used. Your caller, in this case the main function, will initialize both vectors on the stack because they don't fit anywhere. Both of them are 24 bytes. It will also create space for the oversized return value because the caller accepts some return value from the function. It will create this space on the stack, 24 bytes, and pass in the register the pointer to this sum. Remember that the sum, it's not visible there, but the sum is something that exists in the main function. So the caller will basically ask the callee, the add function, to put the sum at this location, will create the space for it and pass the address of this location to the add function. Now, it's quite ugly, but it will also copy the arguments. Officially, there will be copies of arguments being made. Because we pass by value, there is no other chance to do it. So A and B will be copied also on the stack. And what the caller will do, the callee will do, so the add function, it will just look at the arguments A and B, add them together, put the sum in the place that the main pointed to, and that's the end of the story. So for oversized objects, it works a bit different. Passing of arguments happens on the stack. Copies are created. Addresses are passed to the objects that exist on the stack. And most of this talk will be about such objects and what happens then. A main takeaway from it, in a way, everything is returned and passed by value. And you only have 2 types of values. In reality, it's either a full binary representation of an object or a pointer to an object. And there is nothing else. There is really no other kind of passing in C and C++. That's the most technical slide I have, because just so you know, you will see some of those registers appearing, especially the RDI and RSI. I also show examples for what MSVC does. And MSVC uses different registers to pass arguments. But generally speaking, there are registers in your processors, and they are used to pass argument to the functions. In both architectures, ArrayX is used for the return value, so that's good. Let's step onto the main topic, or to the main topic of this talk, returning by value. Nico today showed how it works with forwarding. And there was already a question from one of the members of the audience about whether it always makes sense that sometimes it might disable the return value optimization when you forward something that you return. And that's actually true, it sometimes might, but it was a very complex example. Those are much easier. Imagine you have the simplest scenario possible. You have a function, and you return a temporary from this function, right? So we don't create a named object in the function. We just directly return something, a temporary, in the return statement. And we directly consume this temporary to instantiate a new object. Normally, we are we think, or that's how it should work, that a temporary is created here, then a copy of it is made when you return the object. So it has to be copied into the return object. And finally, there is one more copy when you create some new instance on the receiving side. Now, that hasn't been true for many years already. That's what you have copy-elision for, and the return value optimization. And Michael Tiemann, already in the C++ user journal, observed a long time ago, like really a long time ago, that even then, some compilers do much better than this. So those compilers are smart enough not to create at least one of the copies, because the caller will pass the address of where the return value should be created. And a very smart compiler, a good compiler, will see it and create directly the return object at the location that was passed to it. And that's very good, right? That saves you at least one copy. The same was actually observed by Scott Meyers in More Effective C++. He said that the trick is to not return an object from your function, but to return the arguments to the constructor. And if you do it, most compilers will be able to optimize it away. Let's see how it works nowadays. An example object, it's a string, just like a school book string example. Nothing special about it. It has all special member functions defined, user-defined, so it's totally not trivial. I used my own string instead of using the std string because I could instrument it better. That's the only reason. But, very similar things. Now, what happens when you do something like this? So when you use the tips of how to do it properly, you write a function where an object is returned by actually passing the arguments to the constructor, and try to create a new value from the return object of the function. Most of the compilers will actually optimize away any copy whatsoever. There will be no copy being made. What any sane compiler, and all of the compilers are actually quite sane, will do is emit a code where the address of the str variable will be passed to the caller, and also space for it will be created on the stack, and the caller will be happy to oblige, the callee will be happy to oblige and create directly the object in place on the stack. This way, at least 3 copies or 2 copies are optimized away. So all the compilers do a very good work on it. No problems whatsoever. But as you can imagine, this wouldn't be a good talk or a reason to give a talk if all the compilers work like this. So let's do something more complex. Actually, let's do something more trivial. A trivial string. So something that I already showed, this time extended with the length variable, but the length is just for bookkeeping for me, nothing else really. It's trivial, it's aggregate, actually, and it is oversized. Oversized is my own trait, or actually not trait, it's, I don't know, concept. It's trivial, it should be easy to optimize, like super easy to optimize. There are no constructions there. So what does happen when you run this kind of code? You construct, again, Alice and Bob love C++, this time using the trivial string, which is basically a char array, nothing else, of 32 bytes maximum. Now, luckily, again, good thing happened. The caller will create some space on the stack, pass the address to this space, to the function being called, and the function, the red value, will be happy enough to oblige and create directly the object in place. So good, so far. All the compilers are able to get the target location to the return, or actually to the object that should be constructed as an argument, and there is a full copy-elision known as the return value optimization before. All compilers. besides? Your guess. Which compiler does something else? Thank you. MSVC. That's doing something else. And I needed to remove the header and the footer to fit it on the screen. It's nothing me against MSVC, but that's really crazy what's going on there. MSVC has a different approach. The caller creates two objects on the stack directly. The string object and the temporary for the return value. Both of them 32 bytes, or I think 40 bytes in this case, for no reason whatsoever. It passes the address of the temporary address to the function. So the temporary object address is being passed, and of course the function creates a new object in this location, in the temporary location. Then after returning, the caller creates, or actually copy constructs, as we would say, creates a full binary copy from the temporary into the result. That's crazy. That's crazy because this is C++20 and this is not allowed. So actually the return value optimization should be performed and it should have not happened. It happens nevertheless. There is a copy construction and it shouldn't be there. I was at least surprised when I saw it, because it means in the most trivial case you can imagine, there is no more trivial case. There are no side effects. It's a car array, right? And still, there are two objects being created. It can be very expensive if you blindly trust your compiler. Don't blindly trust your compiler. Check what it does. You might be surprised. Might do what it shouldn't be doing. Why is it so bad? Well, mostly because in C++11, this was fully optional. So in C++11, copy-elision was optional. And what was happening then in C++11, as the standard dictated then, is that a temporary was created when you were returning it. Then the copy or a move of this temporary was kind of skipped when it was passed to the return object, and then skipped or elided once again when initializing some value from it. That's C++11, and it was fully optional, and it was only possible when the copy constructor or the copy or the move constructor existed. Otherwise, the compilers couldn't perform this optimization. In C++17, this has changed. C++17 introduced a rule known as a delayed temporary materialization, which basically means that nothing is created at displays. The arguments are automatically transported one step further. Nothing is created here still. There is no temporary yet created. Only at the final stop, the temporary materializes and your object is created. That's how C++17 sees the things. And it's a must. The compilers should basically implement it, starting with C++17. It's mandatory. You cannot skip it. The cool thing about it is that in C++17, your class doesn't have to have any move or copy constructor for it to work. The not so cool thing is that any side effects of copy constructor or move constructor are ignored and can be ignored, and they are really ignored. That's the surprise sometimes you get when you put printf statements in your constructors and you don't see them printed. That's the side effects being ignored. That's not the end of the story, because this is what's mandated by the standard, but there are other things, much more complex things. And this is actually what Nico was talking about and where the discussion was also about. What about, instead of returning a temporary, we returned a named object, an L value basically. We create a named object in the function, then we return it from the function. Can the compilers do something about it? They can optimize it away. They definitely can. This is the so-called named return value optimizations, and the compilers are allowed to perform it. It's fully optional in C++17 and C++20, but they can do it. Again, there will be a few surprises, I guess. Let's build a very simple function. And we are starting again with the non-trivial string, so with a full copy constructor, copy assignment, move, and the destructor. We create a named L value, something that exists there, must exist in the function. Then to put a bit of play into game, we have a random condition. This is mostly to trick the ICC, because ICC does crazy things. It can predict the branches already at the compilation and optimize for it. So there is a random condition with the 50% of the probability of taking one of the branches. When the result is reassigned inside of the if body in the positive branch. Now, to make it even more difficult, there are two return statements. And I will tell you why it's more difficult in a moment. Again, something that was observed a long time ago. Notice, a really smart compiler could see that the result was basically only feeding the return object and optimize it away. At the time of writing, there weren't any good ideas about how to do it. And there wasn't any compiler that could do it. So Michael Tiemann proposed something inspired, I think, by the old pre-ANSI C, extending the syntax. That's how you would do it in pre-ANSI C when you were declaring the local variables of the function. Didn't get through, luckily. So we don't have to write code like this. So what happens? Now, good thing happened. Again, most compilers, or some compilers, I wouldn't say even if it's most or not, but some compilers are smart enough to see through our tricks, or our trickery. And what they do is they create a value on the stack, an object on the stack, pass the address to this object and tell basically the read value function to create an object there. And some compilers will generate the function in such a way that it will do it. There will be like a total optimization away of all the moves, all the copies on the way, even in this very complex scenario for the compilers. Now, most compilers agree on full copy or actually move elision, because there will be even a move elision here. And yes, there is one compiler which does something else. MSVC again, unfortunately. MSVC does something else. It follows the standard path. So, you know, something is created on the stack. There is basically your object that you are going to feed in the end. And the address of it is passed to the caller, to the callee. Now, the callee is a bit crazy, and read value creates an additional object on the stack, the result object, and basically it creates the full result. And in the follow-up step, it moves the object. It really moves it. So it aligns the copy by moving the object, and it's the task of the function that you call to move the object, the local object that it created, into the target location. So that's what happens. And actually, it's not bad. Think about it, what you want, but it's not bad. Still, there is only one move construction in this very complex scenario. I wouldn't say it's bad. It's actually quite good. I was surprised that some compilers were able to fully align all the copies, all the moves. So MSVC is doing quite good here. It's totally allowed, totally within the standard, no problems whatsoever. Now, the problem starts here. The trivial strings, or the trivial objects, which are so easy to optimize when you pass them to the functions, are apparently not so easy when you return them from the functions. This is where the trouble starts. Again, the same piece of code. We create a string, there is a random condition, two return statements, nothing else. For those of you who don't remember, that was our trivial string, just a char array, nothing scary there. And I must say that some compilers still agree on full optimization or fully optimizing away all the copies, all the moves on the way. So what you will get, again, is just creating a return or the result, or I don't know, a local variable string on the stack, passing the address to it, to the function that you call, and it will nicely create directly without any tricks the object there. Also, the assignment will be directly fed into this object, whatever. So far, so good. Now, I'm not going to ask you which compilers, because you're going to just jump on the easiest answer, and this is not really the correct answer. So it's not only MSVC this time, it's also the optimizing intercompiler, which does crazy things. GCC and Clang do optimize away everything nicely. ICC and MSVC do really weird things. And I'm going to start with the ICC because this is half weird. That can get worse. The ICC, what it does, it starts because basically I think nowadays it's a clone basically of Clang. It starts like any other sane compiler, creates a string object on the stack, passes the address of it to the red value function. The red value function creates a local variable result. Totally not necessary, but it does. It manipulates it, whatever it does, whatever it wants it to manipulate, and then copies it, or copies it. It cannot move it, so it has to copy it back to the string, initializing the variable. This is not bad. This is one copy construction. It's still absolutely within the standard, no pain, right? Now, MSVC actually, rises a bit the stakes here. You're going to see a lot of extra objects. MSVC, first of all, the caller creates a string object in its own stack space and creates a temporary in its own stack space. This temporary is the return object, which it will pass nicely to the callee. Now, the callee thinks different about the temporary that was passed to it and creates one more result, so one more string object in its own stack space. Now we have 3 strings, all of them actually being one object, or should be one object. And then the usual happens. The string is filled in, the result is filled in, and the read value copy constructs the temporary T1, which is totally not visible to you. It's only visible in the assembly. Copy constructs it from the result. Then the function returns, and the caller again copy constructs from the temporary its string. So there are 2 copy constructions on the way that can be very expensive. Again, it's allowed this time. I'm not saying that it's bad. It's allowed, but that's something you should expect also once you've seen this scary face there, right? If it's there, then there will be a copy construction also in a more complex scenario. Now, the crazy thing is that if you remove this return result, a bit of magic happens. It's not as bad for the Microsoft compiler then. Apparently, a double return statement is not that easy to digest. And the same for ICC. You would be surprised, but ICC, I wouldn't say that it avoids a copy construction, but it manages to avoid 20% of it, let's say, or 30%. It's very hard to say because it only does it in one of the if branches, not in the other, but it avoids some copy construction. Now, for the MSVC, it's like eye-opening revelation. MSVC, when there is a no return statement, apparently is able to do it in a sane way. So there is a string still, there is the temporary return object, but the result is directly constructed in this temporary space by your callee. So you are not going to see another object popping on top of it. And that's great. That's great. because you save one copy construction. Now, the strange thing is that this scenario only plays out if the if statement tests negative. So if you don't go into the body of the if. If you go into it, we are back to the base 0, which basically means that there is only in the positive if branch another object constructed. I count it as half a copy construction, because in one branch there is a copy construction, in other not. So let's say that there is 1.5 copy construction with a single return statement. I really had trouble quantifying it for the ICC. I would say it's 0.8 with one return statement, but I didn't put it there. It still does weird things. Lesson: single return is still your friend. We are told differently. We are told that return whenever you want. It's not always true. Compilers are apparently able to reason better about code when there is a single return statement. And that's how it works for those. Now a really, really tricky part when some compilers will really shine and go on. I can imagine, yes. Yeah. As far as, yeah, sorry. As far as I understood, the question was whether the CPU itself is able to elide those copies itself. I guess yes, in some cases it will be. Yeah, it definitely will. When? No idea. But I was also thinking about it, like, why, right? Why would you generate code which makes no sense? So it might. The very tricky part, assignments. Something that, according to common wisdom, cannot be really optimized away. You cannot elide those. It's impossible. There is a string constructed, and then you assign a new value to it. You cannot elide those. No way. That's the lesson we are taught. That's why we should, in such cases, move the value, right? That's what we should do. We should actually do something with this move. I don't think move it will. Yeah, move the value. Yeah, that was correct. So this is a very, very hard scenario for all the compilers, optimizing compilers. There is a return values in the assignment. No way you can do something that makes sense with it. And based on my previous experience with the compilers and a long analysis of what the compilers were doing, I predicted something like this. So I just cannot believe that there will be no copy assignment anywhere. It's impossible. So when it comes to a function that directly returns a temporary, I expected always at least one copy constructor or one move constructor playing its role, depending on whether it's a trivial or a non-trivial type. And for a complex scenario, when I have a function that returns a named object named L value, I expected roughly the same. Expect for the crazy compilers, ICC and MSVC, I expected much worse. I expected 2 copies being made. Now, the good news is it's sometimes much better. Like 3 compilers for a trivial type are able to optimize the whole chain of assignments, copies, whatever. There is nothing. It's all gone. GCC, Clang, and ICC. Now, they cannot optimize away the non-trivial type because there is a non-trivial move there, and you cannot avoid side effects of it. It's not allowed. But this one, they could. How do they do it? Well, very simply. just like any other thing that you've seen. What's being passed to the function that you called is, so first, of course, the original string is being created on the stack. And what's being passed to the callee is the address of this string directly. And the callee directly replaces the binary representation, no strings attached. It skips everything. 3 compilers do that great, and I was really surprised when I saw it. What surprised me even more is that Clang is also able to do it for very complex functions. So Clang is able to optimize also named values in this scenario. Like totally, they're not there. I don't know if you've noticed, but 2 times just also disappeared from one slide to another. ICC for trivial types in complex scenarios just does 1 copy construction, not 2. Now, MSVC still does crazy things, I must say. It's just as it's written there, it performs either 2 times a move construction or 2 times a copy construction, and it's unavoidable. So big chains of copies and moves can be optimized by really smart compilers. And nowadays, I would say that only Clang is this really smart compiler that really can optimize away just about everything. What's even better, really smart compilers and smart compilers can do extremely well for non-trivial types. So for non-trivial types, officially, there is either a copy construction or a move construction somewhere involved. It must be. Well, GCC and Clang can partially optimize this move construction away. So you still have a move constructor, but it's like half of it only that's left over. And that's amazing. So those 2 really shine. How does it work? And it even works because that's really an extra challenge. You wouldn't believe it, but this line of code changes just about everything because the compilers cannot really reason about side effects of printing a string. It's impossible. So it makes it difficult, let's say, for the optimizers. But what happens under the hood for L values and assignment in GCC and Clang is something like this. We start, obviously, by creating on the caller side the string. That must be there. It's our initial string, hello world of C, it says here. I hope it's synchronized with the code on the slides. Hello world of C. Plus plus, yeah, there's still plus plus there. Next, a very strange thing happens. The computer or the program saves the address of the stack allocated memory in one of the registers. It's not needed. It's like totally not needed. Like, why would you ever do it? It saves the address of the stack allocated string in the RBX register. So far, so good. Now, that's the arrows, yes. In the next point, the read val is being called. And the read val, what it does, it creates a new object by overwriting the old one. So it creates it basically in place, in the str place. It just overwrites its binary representation. And that's kind of shocking, because that's not how you programmed it. At this point, somewhere in the middle of calling your function, your string, which you still have there on the stack, which is owned by your caller, doesn't own its memory anymore. It has been erased or overwritten by a new pointer. Who really owns the memory is the RBX at this point. So that's crazy. Now, in the last step, when the callee returns, the caller will free the memory held in RBX. So the move construction happened in 2 different places The move construction partially happened in the function that you called and partially in the caller after the callee returned. That's really surprising. If you really look at the code, I mean, this is like a textbook move constructor, nothing surprising there. If you really look at the code that the assembly generated, what happens is that the delete of the old memory allocated memory happens on the caller side. The reassignment of the variables happens at the callee side, and the rest is not there. Those lines of code don't really exist in the assembly that's generated. So don't write big move constructions. It doesn't make any sense. They will be optimized away anyway. Now, what's the takeaway here? Compilers take advantage of the as-if rule. For those of you who've never heard about the as-if rule, it's very simple. Your compiler is allowed to optimize as much as it wants, as long as the observable effects are as if the code that you have written really executed. If it's there, so if you cannot observe any effects different than what you've written, the compilers are allowed to do it. And some of them will do it very, very aggressively. And Clang really shines like a lighthouse when it comes to it. That's my last takeaway. What are the final, like the summary things I can tell you? Neither passing or returning by value means making a copy, neither it really means moving something. Compilers are really good at optimizing away any of those. If you really want to see what's happening, you have to dive into the generated machine code, unfortunately. And I am afraid also in the Intel optimization manuals at the later stage to know whether some other crazy things do happen, like those that you mentioned. And that's all. So it's time for answers. Thank you very much for listening.